Friends, a long, long time ago, precisely 13.8 billion years ago, everything that ever was or ever will be began with a grand explosion from a point smaller than the period ending this very sentence. However, what is truly mind-boggling is our upcoming journey into the incomprehensible realm that preceded that moment. This was a time when even emptiness wasn't merely the absence of something, where time had not yet begun its count, and where the very concept of existence completely lost its meaning. We will delve into the quantum foam, teeming with virtual particles, into infinite multiverses whose collisions forge new realities, and into mathematical dimensions against which our own universe seems infinitesimally small. Prepare for this extraordinary journey. We are beginning. Imagine the ultimate frontier, the literal end of everything that was before, and simultaneously the birth of everything that will be when. Scientists label this point T0, but this seemingly innocent name conceals the most turbulent and fundamental transformation in all of cosmic history. At this boundary, the very notion of before becomes utterly meaningless, as time, in its conventional sense, did not yet exist. Pause for a moment and truly grasp this. There were no ticking clocks, no aging, no sequence of events. It wasn't just darkness awaiting light. It was the complete absence of duration itself. Mathematical laws break down here, like a computer attempting to divide by zero. Einstein's equations, which flawlessly describe gravity and the space-time continuum everywhere else in the universe, simply cease to function. They yield infinities and impossible answers, as if the universe itself has a "do not enter" sign written in the language of physics. But here's what's truly strange. The moment we're trying to comprehend isn't just the beginning of our universe. It's the beginning of the fundamental framework that allows any beginnings to happen at all. Before this instant, there was no stage for any cosmic drama to unfold. There were no dimensions to measure, no space to fill, no time to flow. Imagine trying to describe the color of something that never reflected light in a place where light itself is impossible. This is precisely what we're attempting when we ask what came before the Big Bang. We're using concepts that only gain meaning after the very moment we're trying to investigate. Nevertheless, modern physics suggests that something profound and significant was happening in this incomprehensible realm. Quantum mechanics asserts that even in perfect emptiness, energy can briefly appear and vanish again. These quantum fluctuations occur constantly in the vacuum of space even today. But if they could happen in absolute nothingness, then perhaps nothing was never truly nothing. The leading theory suggests that our entire universe originated as one such quantum fluctuation. But instead of dissolving, it expanded in less than 1/trillionth of a trillionth of a trillionth of a second. This microscopic bubble of energy expanded at a rate exceeding the speed of light itself, creating space as it grew. Imagine a soap bubble forming on the surface of perfectly still water. Except there is no water. There is no surface. And somehow, the bubble creates both as it grows. The bubble becomes an entire pond, an entire world, everything. This process, called cosmic inflation, explains why our universe appears so uniform in all directions. It also explains why space seems flat rather than curved. However, it raises an even more mind-boggling question that physicists still grapple with. If quantum fluctuations can create one universe from nothing, why would they stop there? The mathematics suggests they wouldn't. It points to something far more extraordinary than a single cosmic beginning. But what we discover next makes our origin story seem simple. When you completely empty a jar, is it truly empty? Most people would likely say yes. However, physics reveals something shocking. What we call empty space is actually teeming with invisible activity. Even in the deepest vacuum between galaxies, where matter is so sparse that you might find only one atom per cubic meter, space itself remains alive with energy. This isn't the nothingness philosophers debate. This is a measurable, detectable, experimentally proven nothingness that refuses to stay nothing. Scientists encountered this astonishing phenomenon when they attempted to cool various substances to absolute zero, striving to extract every minuscule bit of energy from the system. In their investigations, they discovered something that initially seemed counterintuitive. The energy level never drops to zero. Even at the lowest possible temperature, -273 degrees Celsius or -460 degrees Fahrenheit, quantum fields continue to pulsate with what physicists call zero-point energy. This phenomenon can be compared to trying to completely silence a pot of boiling water. No matter how much heat you remove, tiny bubbles continue to form and burst at the bottom. These omnipresent quantum fields permeate every cubic centimeter of space, forming what scientists call the quantum vacuum. Imagine a boundless ocean whose surface appears absolutely serene, but beneath the waterline, countless creatures dart about in movements too swift and minute for the human eye to discern. The quantum vacuum functions on a similar principle. It appears empty, but it continuously generates and annihilates objects on scales smaller than atoms. This is where the most extraordinary part begins. These quantum fields have the ability to borrow energy from the future to create particle pairs that instantly appear, interact for a brief moment, and then annihilate and vanish without a trace. Such events occur trillions of times per second in every tiny volume of space around you right now. The borrowed energy is returned so swiftly that the universe's accounting system never records this temporary debt. Scientists confirm that this is not just a speculative theory by measuring the so-called Casimir effect. When two metal plates are placed very close to each other in a vacuum, the quantum fields between them have less freedom to fluctuate than the fields outside. This creates a tiny but measurable force that pushes the plates together. Empty space, in essence, creates pressure. But here's what will truly make your mind reel. If our observable universe emerged from quantum fluctuations in a vacuum, then what was this vacuum contained within? What initially served as the source of the quantum fields capable of fluctuating? We inevitably arrive at the question of even deeper layers of nothingness. Some physicists hypothesize that mathematics itself may be the fundamental basis of all existence. This isn't about numbers written on paper, but about pure mathematical relationships that exist independently of any physical reality. In this view, our universe consists not of matter and energy, but of mathematical patterns complex enough to possess self-awareness. Other researchers suggest that consciousness plays a key role in shaping reality through observation. Quantum mechanics shows us that particles exist in multiple states simultaneously until something measures them. Could the act of observation by conscious beings have actually collapsed infinite possibilities into the single reality we experience? Right now, particles are constantly appearing and disappearing inside your body. These aren't fantastical special effects from science fiction movies. These are virtual particles, and they are a fundamental element of how reality functions at its deepest level. Every second, quadrillions of these ghostly entities emerge and vanish within your cells, existing for unimaginably tiny fractions of time before dissolving without a trace. Virtual particles may seem like fiction, but they produce real, measurable effects. They are responsible for the magnetic properties of electrons, for how light interacts with matter, and even for the force that prevents atomic nuclei from falling apart. Without virtual particles, atoms could not exist. Chemistry would be impossible, and your presence here would be precluded. Imagine virtual particles as cosmic credit cards. They borrow energy from the quantum vacuum, spend it for a short time to exist, and then return it by disappearing. The shorter their lifespan, the more energy they can borrow. Some virtual particles live for only 10 to the power of -24 seconds. But during that unimaginably brief instant, they can carry a colossal amount of energy. The quantum vacuum is not empty space waiting to be filled. It's more like a cosmic soup where ingredients are constantly dissolving and reforming. Virtual photons carry electromagnetic forces between charged particles. Virtual gluons bind quarks within protons and neutrons. Virtual particles of every type arise and vanish, creating an invisible foundation beneath visible reality. Here's the most mind-boggling part. These elusive, ephemeral virtual particles can sometimes become real. When enough energy is pumped into the quantum vacuum, which is essentially the fabric of space-time, pairs of virtual particles, normally destined for instant annihilation, can separate before they mutually destroy each other. Under such conditions, they become permanent, tangible additions to reality. This phenomenon is particularly evident around black holes, where intense gravitational fields provide the necessary energy for virtual particles to escape their quantum debt, the obligation to immediately disappear. The distinguished physicist Stephen Hawking discovered that black holes gradually evaporate by turning virtual particles into real ones. In the immediate vicinity of the event horizon, a black hole's point of no return, pairs of virtual particles separate under the influence of powerful gravity. One particle irreversibly falls into the black hole, while its partner escapes into cosmic space as real radiation. In the process of such radiation, the black hole loses energy, slowly shrinking in size until it completely vanishes in a final dazzling flash of light. This process suggests something profound and fundamental about the very nature of existence. If virtual particles can transform into real ones when given adequate energy, and if our entire vast universe could have originated as a simple quantum fluctuation, then the boundary between the real and the virtual becomes astonishingly thin, almost indistinguishable. Some physicists hypothesize that our entire universe, in a sense, may still be virtual, borrowing its energy from an even deeper level of reality that we have yet to discover or comprehend. In this view, everything we call real, from giant planets to individual people and distant galaxies, exists, as it were, on loan, like a grand cosmic quantum fluctuation that began 13.8 billion years ago. However, if virtual particles can give rise to our universe, they can just as easily create others. The same quantum vacuum that constantly spawns fleeting virtual particles around us could very well be generating entire cosmoses in regions we are currently unable to detect or explore. The implications of this realization lead us to a possibility that overshadows even our own grand cosmic beginning. Our universe may be just one bubble in an infinite cosmic bath. Right now, as you intently read these words, countless other versions of you might be reading slightly different versions of this sentence in parallel universes. Some of these universes are almost identical to ours, differing only by the minuscule position of a single electron. Others are so whimsical and strange that the fundamental laws of physics work completely differently than in our reality. The multiverse theory emerged when physicists realized that quantum fluctuations are not obligated to create only one universe. If the quantum vacuum could give rise to our cosmos, it could just as likely give rise to others. In fact, mathematical calculations suggest that it should produce other universes constantly and infinitely, much like soap bubbles form on the surface of a boundless sea. Each such universe would begin with its own Big Bang, expand through its unique version of cosmic inflation, and develop its own distinct properties. Some might have stronger gravity, leading to stars burning out faster and dying earlier. Others might have weaker electromagnetic forces, preventing atoms from forming at all. Most would likely be barren wastelands where no complexity ever develops. But some might contain forms of life we cannot even imagine. Imagine an eternal cosmic ocean where every possible wave eventually forms. Our universe is just one wave in this boundless ocean. It is temporary and unique, but not special. The multiverse doesn't care about our existence, just as the ocean doesn't care about the individual drops of water that make up its volume. But here's where it becomes truly staggering. Some versions of multiverse theory propose the existence of an infinite number of universes, which inevitably means that every possible variation of reality exists somewhere. There is a universe where dinosaurs never went extinct and continue to reign on Earth. There is a universe where gravity repels instead of attracts, overturning all our notions of physics. There is a universe where you decided to become a brave astronaut instead of reading this text. These parallel realities are not just fantasies from science fiction works. They naturally arise from our most precise mathematical descriptions of quantum mechanics and the theory of cosmic inflation. When you solve the equations governing the behavior of the quantum vacuum, the creation of an infinite number of universes emerges as an inevitable consequence. The implications of this realization are breathtaking and terrifying at the same time. If infinite universes exist, then every possible tragedy and every triumph is happening somewhere right now. Every book that could be written already exists in some universe. Every scientific discovery that could be made has already been made in countless parallel realities. Some physicists go even further, suggesting that the multiverse itself may be just one level in an even grander hierarchy. Perhaps there are infinite multiverses, each containing infinite universes, layered in realities that extend far beyond our limited human comprehension. However, if the concept of parallel universes has a basis, their separate existence may not be eternal. Quantum mechanics allows for the possibility that these worlds could collide, merge, or influence each other in ways humanity is only beginning to comprehend. The cosmic microwave background radiation, pervading cosmic space, might well contain subtle traces of ancient collisions with other universes that occurred billions of years ago. This hypothesis leads us to an even more radical thought about what existed before our own cosmic beginning. What if our Big Bang wasn't a moment of genesis, but merely another reboot? Imagine a cosmic phoenix that dies in flames every trillion years, only to be reborn from its own ashes. Some physicists hypothesize that our universe follows precisely such a pattern, passing through infinite cycles of expansion, subsequent collapse, and new rebirth. In this view, the Big Bang is seen not as creation from absolute nothingness, but as a transformation from something that existed before it. The cyclic universe model posits that our cosmos has been expanding for billions of years, which is what we currently observe. However, eventually, this expansion will slow down, stop, and then reverse. Gravity will ultimately triumph, pulling every galaxy, every star, every atom back into a single cosmic collapse known as the Big Crunch. But here's the key point. Instead of ending in complete destruction, the Big Crunch transforms into a Big Bang. The universe bounces back from a state of maximum compression, erupting into a new cycle of expansion. Time does not cease its flow during this transition. It continues through what physicists call the cosmic bounce. Imagine a cosmic trampoline. Our universe rushes towards the surface of this trampoline, accelerating as it approaches a state of maximum density. Then the elasticity of the trampoline comes into play, launching the universe back into a new phase of expansion. Each such bounce generates an event that, from within, appears as a Big Bang, though in reality it is merely another oscillation in the eternal rhythm of existence. This model resolves several long-standing mysteries that plague the traditional Big Bang theory. It provides an explanation for why our universe appears so uniform in temperature and density, without requiring the incredibly rapid inflationary period that standard models necessitate. It also eliminates the uncomfortable question of what exactly caused the Big Bang. As in this concept, there is no absolute beginning, only infinite cycles. Recent observations of our universe's accelerating expansion, driven by mysterious dark energy, would seem to rule out the possibility of a future Big Crunch. However, cyclic universe theorists have adapted their models to include dark energy. They suggest that the force of dark energy changes over cosmic timescales, eventually reversing its direction from accelerating expansion to accelerating contraction. In some variants of cyclic cosmology, each cycle lasts approximately 1 trillion years. Our current cycle began 13,800 million years ago, making us relatively young in a cosmic sense. We still have hundreds of billions of years ahead of us before expansion stops and collapse begins. However, each cycle may not be perfectly identical to the previous one. Small variations can accumulate over cosmic generations, making each universe slightly different from its predecessor. Perhaps consciousness and intelligence evolve further in each subsequent cycle, as information is somehow transferred from one cosmic generation to another. Other cyclic models suggest that parallel universes alternately expand and contract, like cosmic pistons in an infinite engine. While our universe is in an expansion phase, others are contracting. While other worlds explode into new Big Bangs, we are moving through an expansion phase. These ideas lead to the thought that the question, what came before the Big Bang, has a simple answer: the previous cycle. But this only deepens the mystery. What then started this infinite cycle at all? And can the cycles ever end? Reality may contain 6 invisible dimensions that are curled up around every point in space. Right now, as a person sits and reads these lines, they are surrounded by dimensions they cannot see, touch, or directly perceive. According to string theory, these hidden dimensions are curled up so tightly that they exist at every point in our familiar three-dimensional world, but on such infinitesimally small scales that even our most powerful microscopes cannot detect them. Imagine an ordinary garden hose seen from a distance. From this distance, it appears as a one-dimensional object, like a simple line. But upon closer inspection, it becomes evident that it possesses hidden circular dimensions curled up around its main length. String theory postulates that our universe functions on a similar principle. What we perceive as 3 spatial dimensions and 1 time dimension may actually represent only 4 dimensions, unfolded from a much larger reality that contains a total of 10 or even 11 dimensions. These additional, invisible dimensions are not simply empty space. They are dynamic, constantly changing arenas where the fundamental forces of nature play out. The forces of gravity, electromagnetism, and nuclear interactions in our familiar dimensions directly depend on how these hidden dimensions are curved and twisted. Within string theory, the tiniest building blocks of the cosmos are not point particles, but incredibly tiny vibrating loops of energy called strings. These strings are unimaginably small, their length being approximately 10 to the power of -35 meters. This is so minuscule that if an atom were enlarged to the size of our solar system, a string would still be smaller than an ordinary tree. Each unique vibration pattern of these strings gives rise to what we perceive as different elementary particles. For example, an electron is a string vibrating in a certain way. A photon is the same string, but vibrating completely differently. A quark is yet another distinct vibration pattern. This can be compared to a grand cosmic symphony, where each individual note corresponds to a unique fundamental particle. String theory also hypothesizes that the Big Bang may have been triggered by collisions between higher dimensional objects known as branes. Our entire universe could be a 3-dimensional membrane floating freely in higher dimensional space, like a thin soap film on the surface of a multi-dimensional bubble. When 2 such branes collide in this higher dimensional realm, the impact releases a colossal amount of energy into each of them. From our perspective, being inside one of these branes, this sudden release of energy is perceived as the Big Bang itself. Time and space, as we know them, begin their existence at the moment of this collision. Yet the branes themselves existed long before it. This brane collision model offers an explanation for several long-standing mysteries concerning the birth of our universe. For example, it explains the striking uniformity of the cosmic microwave background radiation without requiring the hypothesis of superluminal inflation. Furthermore, it implies that the event we call the Big Bang was actually a transition from one brane state to another, rather than an act of creation from absolute non-existence. Moreover, hidden dimensions may even contain parallel branes, which, in turn, may host other universes. These parallel realities could be just 1 millimeter away from us in higher dimensional space, yet remain absolutely inaccessible because we are trapped on our own 3-dimensional brane. This leads to an even more mind-boggling possibility regarding the true nature of cosmic creation. Somewhere in the vast expanses of the cosmos, new universes are born every second. As you immersed yourself in reading this text, countless Big Bangs have already occurred in distant regions of space. Each of them gives rise to an entire cosmos filled with billions of galaxies. This is not fiction from science fiction novels. It is a logical consequence of the theory of eternal inflation, one of the most successful and widely accepted models in modern cosmology. Traditional inflation theory offers an explanation for how our universe expanded from subatomic to cosmic scales in the first fraction of a second of its existence. However, eternal inflation suggests that this process never stops. It simply moves from one place to another, creating an endless sequence of so-called pocket universes in an ever-expanding multiverse. Imagine a pot of boiling water where bubbles continuously form and detach from the surface. Each such bubble represents a separate universe, similar to ours, with its own unique space, time, and set of physical laws. The boiling water in this comparison symbolizes the inflationary field that fills the multiverse, eternally giving rise to new bubbles of reality. Our observable universe is merely the interior of one such bubble. The Big Bang was not the beginning of everything, but merely the moment when our local region of space ceased inflation and began the slower expansion we observe today. But beyond our bubble, the cosmic inflationary field continues its exponential growth, occasionally spawning ever more new pocket universes. This process has neither beginning nor end. Even if inflation began at some point in the past, once it starts, it produces infinite future time and infinite space. The multiverse expands at such an incredible rate that no matter how many pocket universes form, there is always room for infinitely more. Each pocket universe can possess different physical constants. In some, gravity might be significantly stronger, leading to stars burning out quickly. In others, the electromagnetic force might be weaker, preventing complex chemistry from forming. Most pocket universes would likely be sterile and uninhabitable, but occasionally one turns out to have the right conditions for complexity and life to arise. The distances separating these pocket universes are truly astonishing, surpassing any bounds of human imagination. They are separated by regions of space that are still inflating, meaning they are expanding at a speed greater than the speed of light. Even if a hypothetical traveler could travel forever at the speed of light, they would never be able to reach another pocket universe, because the space between them and their destination expands faster than they can traverse it. But here's where the truly mind-boggling realization begins. In a multiverse, in a state of eternal inflation, every conceivable universe exists somewhere. Thus, one can imagine a pocket universe where the laws of physics allow for faster-than-light travel. There exists another where the flow of time is reversed. There is even one where the fundamental constants are tuned with such incredible precision that black holes naturally evolve into conscious beings. This infinite multiplication of realities raises profound questions about the very essence of existence. If every potentially possible universe truly exists, then the concepts of possibility and actuality merge. Everything that can happen inevitably happens somewhere in this eternal multiverse. Some physicists express concern that the concept of eternal inflation makes science impossible, as it predicts that absolutely everything can happen somewhere. Others, however, embrace it as the most elegant explanation for why our universe seems so perfectly tuned for the emergence of complexity and the development of life. However, even eternal inflation leaves an even deeper mystery unsolved. At the very edge of the Big Bang, mathematics itself ceases to function. Physicists have managed to trace the history of our universe back to a tiny fraction of a second after its inception in the Big Bang. They are capable of describing in detail the formation of the first atomic nuclei, the birth of the first stars, and even the moment when cosmic space became transparent to light. But there is one boundary they cannot yet cross: the very moment when all their equations yield nonsense. This boundary is called the Planck epoch. It spans the time interval from t0 to approximately 10 to the power of -43 seconds after the Big Bang. During this unimaginably short period, The universe was so hot and dense that quantum effects completely dominated gravity itself. Space and time acquired a grainy and indeterminate structure, like a photograph magnified to such an extent that individual pixels become visible. At the Planck scale, the smooth fabric of space-time described by Albert Einstein breaks down into a kind of quantum foam. Distances smaller than the Planck length, which is about 10 to the power of minus 35 meters, lose all meaning. Time intervals shorter than the Planck time, which is about 10 to the power of minus 43 seconds, cannot be measured even in principle. Imagine trying to use a ruler made of atoms to measure something smaller than an atom itself. In this case, the ruler itself becomes the limiting factor. Similarly, when we try to explore the Planck epoch, our fundamental concepts of space and time become a limitation. We are trying to use space-time to understand the origin of space-time itself. This gives rise to what physicists call the boundary problem. Every equation in physics implies that space and time exist as a kind of background stage on which events can unfold. But at the moment of the Big Bang, such a stage did not exist. The stage itself was created simultaneously with the very concepts of moment and creation. Einstein's theory of general relativity, which is our best theory of gravity and spacetime, predicts that all matter was compressed into a mathematical point of infinite density called a singularity. However, infinities in physics usually signal that a theory has reached its limits of applicability. In reality, there are no true infinities. It merely means that our mathematical descriptions stop working. Quantum mechanics, in turn, suggests that the singularity should be replaced by something else. Perhaps it was a region of maximally possible density, where space and time become quantized, like energy levels in an atom. But we do not yet have a complete theory of quantum gravity capable of describing this region. Some physicists suggest that asking what happened before the Planck epoch is equivalent to asking what is north of the North Pole. Time itself may have a boundary, a first moment that nothing preceded. In this view, the Big Bang represents the absolute beginning of temporal existence. Others, however, propose that time may be emergent, meaning it arises from more fundamental, timeless processes. Just as temperature arises from the chaotic motion of countless atoms, time may emerge from quantum interactions in a deeper reality that does not experience duration in our familiar sense. This problem, related to the boundaries of existence, points to one of the deepest mysteries hidden within all modern science, the unbreakable link between information and existence itself. Before the universe began its grand journey, it remains unclear exactly where the information absolutely necessary for its creation was stored. Every minuscule particle that makes up your body, every single atom in every shining star, every quantum state in every boundless galaxy, all of them contain specific information. Your unique DNA carries exhaustive information about your biological structure. The quantum states of electrons in your brain store information about your thoughts and memories. Thus, the universe at its core consists precisely of information. But where did all this information originally come from? Consider, for example, the simplest hydrogen atom, which is the most basic element in the entire vast cosmos. Even this seemingly uncomplicated system contains precise information about the electron's energy level, the direction of its spin, and its orbital characteristics. If you multiply this by every atom present in every galaxy, the amount of information in our observable universe becomes truly astronomical, surpassing all human comprehension. Traditional physics tends to view information as something encoded into already existing matter and energy. However, quantum mechanics reveals something extremely strange and unexpected to us. Information itself may be far more fundamental than the matter and energy that carry it. In quantum systems, it is the information about a particle state that determines what kind of particle it is, not the other way around. This leads to a paradox that touches upon the very essence of cosmic origin. If our universe arose from quantum fluctuations in absolutely empty space, Then where did the informational content of these very fluctuations come from? Empty space should not have contained the vast libraries of information necessary to define the properties of billions of galaxies. Some physicists hypothesize that information is conserved, just like energy. This means it can never be created or destroyed, only transformed from one form to another. In this view, the information in our universe must have existed before the Big Bang in some form. But this only pushes the mystery to an even deeper level. What exactly stored all this information before space and time came into being? The holographic principle offers a mind-bending solution. It suggests that all the information contained within a three-dimensional region of space can be encoded on the two-dimensional boundary of that region. This is similar to a hologram, which contains a complete three-dimensional image on a flat surface. Applied to cosmology, this principle means that all the information in our universe could be encoded on its boundary, on the cosmic horizon. From this perspective, our three-dimensional reality might very well be a projection of information stored on a distant two-dimensional surface. We could be existing inside a cosmic hologram without realizing it. However, this still doesn't answer the question of where the information on the boundary originally came from. Some theorists suggest that information is truly fundamental, existing independently of space, time, matter, and energy. In this view, physical reality arises from pure information processing, like a cosmic computer running the program we call the universe. If information is the fundamental essence, then asking where it came from is akin to asking why mathematics works. Information simply exists as a basic feature of reality, requiring no further explanation. Our universe would be one of the possible arrangements of this primal information, selected by processes we are not yet able to fully comprehend. This information-based view of reality points to an even stranger possibility regarding the nature of existence itself. True nothingness, perhaps, is simply impossible. Imagine an absolutely perfect void. No matter, no energy, no space, no time, no fields, no forces, no possibilities for anything to exist. This is precisely what most people consider absolute nothingness. However, quantum mechanics suggests that such a state cannot exist even in principle. The reason for this lies in the uncertainty principle, one of the fundamental laws governing reality at its smallest scales. This principle states that it's impossible to simultaneously know both the exact position and the exact momentum of any particle. But its application isn't limited to just particles. It also extends to energy and time, as well as the quantum fields that fill all space. In a perfectly empty region with zero energy, you would know the energy precisely. But the uncertainty principle forbids this perfect knowledge. Therefore, energy must fluctuate, borrowing from the quantum vacuum and returning to it in a cosmic shell game that never stops. These fluctuations are not if quantum fluctuations, these fleeting disturbances of energy, are capable of manifesting in empty space. Then it is logical to assume that they should be able to arise even in the complete absence of space itself. In other words, even absolute nothingness, if it could attain being, would still be subject to quantum uncertainty. This means that nothing would remain static. It would inevitably fluctuate, giving rise to something from nothing, thanks to the fundamental laws of quantum mechanics. Such fluctuations in pure nothingness would not be limited to just tiny particle pairs. The uncertainty principle, a key postulate of quantum physics, allows for the emergence of colossal fluctuations, provided their duration is incredibly fleeting. A fluctuation massive enough to create an entire universe could well be permissible if it returned its borrowed energy quickly enough, disappearing as swiftly as it appeared. But this is precisely where the concept of cosmic inflation comes into play, offering a fascinating explanation. If a universal fluctuation arising from nothing began to inflate, or expand, at an incredible rate, it could grow beyond its own quantum wavelength before the time limit for returning the energy expired. Once this happens, the fluctuation transforms from an ephemeral, borrowed existence into a real and permanent being. Think of it as using a quantum credit card with no spending limit, but with immediate payment demands. Most purchases are instantly canceled, but sometimes it happens that a purchase becomes so massive that it exceeds the system's ability to cancel it. The debt becomes real, but so does the acquisition. Our entire universe may be the result of just such a quantum fluctuation that grew to such proportions that it could no longer be canceled. From this perspective, existence itself is a kind of cosmic accident, a quantum hiccup that inflated beyond the point of no return. However, if one universe can arise from pure nothingness through fluctuation, then it is logical to assume that other universes must constantly appear in the same way. Pure nothingness, if it ever existed, would be inherently unstable, continuously generating an infinite number of realities through quantum uncertainty. This raises a profound philosophical and scientific question. If nothingness is fundamentally impossible, then has something always existed? The answer to this question leads us to consider the role of consciousness itself. What if the universe needs observers in order for it to exist? Quantum mechanics presents us with a truly puzzling enigma that has tormented physicists for almost a century. According to its tenets, particles exist in multiple states simultaneously until the moment of measurement, distributed in so-called clouds of possibilities. However, at the very instant someone makes an observation, these possibilities collapse, shrinking into definite realities. The act of observation, therefore, literally creates the observed reality. This is not merely a philosophical speculation. It is an experimentally verified scientific truth. Electrons can be in multiple places at once until they are detected. Photons can travel multiple paths simultaneously until they are measured. The quantum world remains fundamentally indeterminate until a conscious mind observes it. But here's where the truly mind-boggling question arises. If observation causes reality to be created, then what observed the universe before conscious beings evolved? How could the universe exist for billions of years before the first intelligent beings appeared, capable of collapsing its quantum possibilities into definite states? Some physicists have hypothesized that consciousness itself may be a fundamental element of the cosmos, not something that arose from a complex arrangement of matter, but something that was present from the very beginning of time. In this view, the Big Bang was not just an act of creating matter and energy, but the first moment when cosmic consciousness began to observe itself. Think of reality as a vast quantum computation, where consciousness acts as the processor, transforming possibilities into actuality. Without consciousness to run this program, the universe would remain a mere cloud of unrealized potential, forever suspended in a state of quantum superposition. This idea suggests that what existed before the Big Bang was pure consciousness without any content, an infinite potential awareness that had nothing yet to be aware of. The Big Bang, therefore, would represent the moment when consciousness began to observe itself, creating space, time, and matter through the act of self-observation. However, if consciousness actively shapes reality through the process of observation, then it becomes evident that diverse types of consciousness are potentially capable of generating different kinds of actuality. Human consciousness, possessing unique patterns of attention and modes of measurement, structures the universe in a way that inevitably reflects our own cognitive mechanisms. At the same time, hypothetical alien consciousness, equipped with entirely different sensory systems and mental templates, might well perceive the existence of a fundamentally different universe. Such a concept opens the door to extraordinary reflections on parallel realities. Every conscious decision an individual makes could, in essence, split the universe, generating new branches in which different choices unfold. Every observation made by a subject is capable of selecting one specific reality from an innumerable multitude of quantum possibilities. Human consciousness does not simply passively observe the universe. It actively participates in its continuous co-creation, occurring from moment to moment. Some interpretations of quantum mechanics propose that all potentially possible realities coexist simultaneously within a vast multiverse. But it is consciousness that chooses which of these branches it experiences. From this perspective, before the Big Bang, all potential universes existed as pure, unrealized potential. The emergence of consciousness marked the creation of the first definite reality, choosing one possibility from an infinite quantum menu. If consciousness is fundamental, rather than an emergent property, then it is perhaps the only thing that does not need to be created or explained. It simply is, like existence itself. The universe, therefore, may be consciousness exploring its own infinite potential through the experience of space, time, and matter. This approach leads us to an even more radical hypothesis regarding the connection between mind and mathematics. What if reality is literally made of mathematics? Right now, a person might think they are reading words made of matter, sitting on a physical chair, breathing real air. But according to the mathematical universe hypothesis, they are actually experiencing mathematical structures so complex that they have achieved self-awareness. An individual is not made of atoms and molecules, they are made of numbers and equations that have learned to think. This is not just a metaphor or analogy. MIT physicist Max Tegmark seriously proposes that mathematical existence and physical existence are identical. Every electron, every photon, every quantum field, these are actually mathematical objects. The universe doesn't just follow mathematical laws, it is mathematics itself. It's worth considering what mathematics truly is. When a person uses algebra to describe motion, they are not creating an approximation of reality, they are discovering the actual structure of reality itself. Equations don't describe something else, they are that something else. Physical objects are mathematical objects that have reached sufficient complexity to interact with themselves. This idea resolves a puzzle that has plagued scientists for centuries. Why is mathematics so unreasonably effective at describing the natural world? The answer is exceedingly simple. Mathematics works perfectly because reality is mathematics. We are not discovering mathematical approximations to physical laws. We are discovering the mathematical structures that constitute existence itself. But here's where the concept becomes truly mind-boggling. If our universe is one mathematical structure, then every possible mathematical structure must also exist as a physical universe. There is a universe based on different geometries, where space has 4 dimensions instead of 3. There is a universe where mathematical constants have different values, causing physics to work differently. Every mathematical theorem, every possible equation, every conceivable logical system corresponds to a real universe somewhere in the ensemble of all mathematical reality. Our universe is described by the specific mathematics we observe, but countless other universes are described by different mathematics. From this perspective, the Big Bang was not the creation of matter and energy from nothing. It was the moment when a specific mathematical structure became complex enough to support moments of observation, conscious experiences embedded within the mathematical structure. A person is not a biological being observing a mathematical universe. They are a mathematical pattern that has achieved self-awareness. This explains what existed before the Big Bang. Mathematics itself existed in all its infinite complexity and possibility. The ensemble of all mathematical structures was complete and eternal, containing every possible universe as a subset. Our Big Bang represents the moment when observers first appeared within one specific mathematical structure. Time in this view transforms into an illusion. The mathematical structures underlying reality exist outside temporal frameworks, much like eternal geometric theorems. Human perception of time is due to our being part of structures that contain temporal sequences. However, from an external perspective, all moments exist simultaneously. The mathematical universe hypothesis asserts that consciousness is not something separate from mathematics, but rather an internal sensation of complex mathematics. As mathematical structures achieve sufficient intricacy and self-reference, they give rise to subjective experience. This leads us to confront one of the deepest mysteries of all cosmology. Dark energy should not exist, yet it is tearing our universe apart. In 1998, astronomers made a discovery that overturned all physicists' notions of cosmic destiny. The expansion of the universe was not slowing down under the influence of gravity, but on the contrary, accelerating. Something was pushing galaxies apart with an ever-increasing force, and no one had the slightest idea about the nature of this force. This mysterious force was named dark energy, and it constitutes about 70% of all that exists. Dark energy is invisible, undetectable except for its effect on cosmic expansion, and it completely contradicts our understanding of how energy should behave. Ordinary energy is diluted as space expands, like perfume spreading through a room. Dark energy, on the contrary, intensifies. The leading explanation involves the cosmological constant, a number Einstein added to his equations to keep the universe static. He later called this his greatest blunder when observations showed the universe was expanding. However, the recent discovery of accelerating expansion suggests that Einstein's blunder was actually a profound insight into the nature of reality. The cosmological constant represents the energy density of empty space itself. Even a perfect vacuum contains energy, and this vacuum energy creates a repulsive force that pushes space apart. It appears as if the universe is filled with an invisible substance that causes space itself to expand. But here's the problem that keeps physicists awake at night. When you calculate how much vacuum energy empty space should contain using quantum mechanics, you get a number that is 10 to the power of 120 times larger than what we observe. This is not a small error. This is the worst prediction in the history of science. If quantum mechanics is right about vacuum energy, our universe should have expanded so rapidly that atoms couldn't form, stars couldn't shine, and galaxies couldn't exist. The fact that we are here to ask these questions means that somehow the universe tuned its vacuum energy to a value incredibly close to zero, but not exactly zero. This fine-tuning is so precise that it seems impossible for it to have happened by chance. It's like balancing a pencil on its tip for billions of years while earthquakes shake the table. And yet, somehow, the universe achieved this impossible balance. Some physicists suggest that what we call dark energy is not vacuum energy at all, but some other field that mimics the effects of the cosmological constant. Others suggest that the laws of physics themselves may evolve over cosmic timescales, with the cosmological constant changing as the universe ages. The multiverse offers another explanation. If there are infinite universes with different vacuum energies, most of them would expand too quickly or collapse too quickly for complexity to develop. We observe a universe with the correct cosmological constant because we could not exist in universes with the wrong value. But this raises an even deeper mystery. Why do the fundamental constants of nature seem perfectly tuned for the existence of complexity, consciousness, and life? The answer may reveal the deepest mystery of what came before our cosmic beginning. The force that appears to be tearing our universe apart may well be nothing other than an echo of its own genesis. Dark energy remains to this day one of the most grandiose and inexplicable mysteries of modern physics. Yet its true origin story may have been laid down in the very first moments after the so-called Big Bang. A number of distinguished physicists hypothesize that dark energy is in fact a fossil energy trace of cosmic inflation, a phenomenally rapid expansion that stretched our universe from subatomic scales to truly cosmic dimensions in the first fraction of a second of its existence. During inflation, space itself expanded at a rate exceeding the speed of light, and this process was driven by a quantum field that scientists called the inflaton. This field contained a colossal energy density, sufficient to form all the matter and energy we observe today, once inflation finally ended. But what if inflation never completely ceased? What if a tiny, barely perceptible remnant of the inflaton field still pervades all cosmic space? This residual trace would probably not possess enough power to cause rapid inflation, similar to what occurred in the early universe. Yet it could very well provide the gentle but constant push that accelerates cosmic expansion today. Thus, dark energy may be the last breath of the grand force that gave birth to our universe, still echoing in the boundless expanses of the cosmos almost 14 billion years later. Imagine this phenomenon as a faint ripple appearing on a perfectly still pond surface after a stone has been thrown into it. Long before the stone finally sinks to the bottom and the initial splash completely subsides, tiny waves continue to spread in all directions. Dark energy may be precisely such a last ripple from the cosmic inflation that caused our universe to come into being. But further reasoning leads to even more astonishing conclusions. If dark energy is indeed derived from residual inflationary energy, then as the universe expands, it should gradually decrease. Eventually, it should completely disappear, allowing gravity to once again slow cosmic expansion. In such a case, our current phase of acceleration would be merely a temporary phenomenon. This would be a transitional period between a past dominated by matter and a completely unknown future. Other scientific theories suggest that dark energy, on the contrary, may not decrease but increase. If this hypothesis is true, then cosmic expansion will accelerate faster and faster until it eventually tears apart galaxies, then solar systems, atoms, and even space itself. This catastrophic scenario, known as the Big Rip, will end the existence of our universe in approximately 22 billion years, when expansion becomes infinite and the very fabric of space-time is ripped to shreds. There is also an alternative viewpoint. Dark energy may oscillate, alternately pushing expansion and resisting it. Such oscillations could give rise to cycles of acceleration and deceleration, possibly even leading to future periods of cosmic contraction and new Big Bang events. The most disturbing and terrifying possibility is that dark energy represents a fundamental instability inherent in the quantum vacuum itself. Our current vacuum state may turn out to be a so-called false vacuum, temporarily stable but destined to decay into a lower energy state. When this happens, a bubble of true vacuum will begin to expand at the speed of light, destroying everything in its path and completely rewriting the laws of physics. This vacuum decay may have already begun somewhere within the observable universe. The bubble of destruction would be completely invisible until it reached us, moving at the speed of light and erasing reality as it expands. We would never see it coming. Dark energy forces us to confront the astonishing possibility that the apparent stability of our universe is merely an illusion, a temporary calm before an inevitable storm that will change or destroy everything we know. The universe, paradoxically, seems specifically designed for our existence, and no one knows for sure why. Right now, each of us exists because of the most incredible cosmic coincidence in all of scientific history. The forces that govern reality are balanced with such astonishing precision that changing any of them by even an infinitesimally small amount would make stars impossible to form, atoms unstable, or completely forbid the existence of any complexity. Consider, for example, gravity, which is the weakest of the fundamental forces. If gravity were just slightly stronger, stars would burn out in millions of years instead of billions, never allowing life to evolve. If gravity were slightly weaker, stars would never form at all, as gas clouds would be unable to collapse under their own weight. The electromagnetic force demonstrates the same seemingly impossible precision. Make it slightly stronger, and electrons would bind so tightly to atomic nuclei that chemistry would become impossible. Make it weaker, and atoms would fall apart, making molecules and complex structures forbidden by physics itself. The strong nuclear force, which holds atomic nuclei together, is tuned even more precisely. Change it by just 5% in either direction, and you eliminate either carbon or oxygen from the universe. Without both of these elements, the chemistry of life becomes utterly impossible. But the most striking example, without a doubt, is related to the cosmological constant, which, as is known, governs dark energy. We have already mentioned that, according to the predictions of quantum mechanics, This constant should be 10 to the power of 120 times greater than what we actually observe. And yet, in some incomprehensible way, it is tuned almost exactly to a zero value, which allows our universe to exist for billions of years. Otherwise, if it were different, the universe would expand so rapidly that matter would never be able to coalesce and form structures. The probability that all these constants randomly fell within such narrow ranges, allowing for the existence of complexity, is essentially zero. This can be compared to trying to throw a dart from 1,000,000 miles away and hitting a target no bigger than a single atom. The probability of such an event is so minuscule that it can be considered impossible without exaggeration. This so-called fine-tuning problem forces us to ask very uncomfortable questions about the very nature of reality. Is it possible that someone or something set these constants deliberately? Do we live in a kind of engineered universe created specifically for consciousness and complexity to arise? Most physicists tend to reject the idea of intelligent design, but they are left with equally dizzying alternatives. The multiverse hypothesis, for example, suggests the existence of an infinite number of universes, each with random physical constants. Most of them would likely be barren wastelands, but we observe a finely tuned universe precisely because we simply couldn't exist in universes with unsuitable constant values. The anthropic principle extends this idea further, asserting that the universe must be compatible with consciousness because conscious observers are here to explore it. We don't observe random physical constants because random constants typically don't produce observers. But some physicists suggest that consciousness itself may play a role in selecting physical constants through the effects of quantum measurement. If moments of observation help collapse quantum possibilities into definite realities, then the act of observation may literally tune the universe to be compatible with observers. This leads to the most radical possibility of all, that consciousness and physical reality co-evolve, shaping each other in ways we are only beginning to understand. Imagine that other universes could be crashing into ours right now. As you read these words, our universe may be slowly, as if in slow motion, colliding with parallel realities, leaving faint imprints across the cosmic sky. These collisions, of course, would not result in the destruction of galaxies or planets. They would occur so gently and imperceptibly that only the most sensitive instruments would be able to detect their traces. According to the theory of eternal inflation, our universe is just one of countless bubbles in an infinite foam of realities. Most of these bubble universes are expanding away from each other at speeds greater than the speed of light, making any contact between them absolutely impossible. However, sometimes two bubbles can form close enough to each other for their boundaries to touch before cosmic expansion pulls them apart. When the boundaries of universes collide, they don't explode like car crashes. Instead, they interact through quantum fields that exist on both sides of the collision zone. These field interactions would release energy that propagates through both universes in the form of gravitational waves and radiation from within our universe. Such a collision would manifest as a circular pattern in the cosmic microwave background radiation. This is the ancient light that fills the sky, the afterglow of the Big Bang. The collision zone would create a subtle warm or cold spot in this radiation, a kind of cosmic bruise marking the place where another reality touched ours. Several research groups have claimed to have detected such patterns in the cosmic microwave background data, although other scientists dispute these findings. The signatures are so subtle that they are extremely difficult to distinguish from random fluctuations or instrumental noise. Perhaps we already have evidence of parallel universe collisions, but we cannot be sure yet. If parallel universe collisions are indeed real, they could occur multiple times as our cosmic bubble collides with various neighbors during its expansion. Our sky, therefore, may contain multiple collision signatures from different parallel realities. Each would mark a brief moment of contact with an alternative cosmos. But here's the truly mind-boggling possibility. If universe collisions can occur, they can also exchange information across the boundary. Quantum fields could carry data from one universe to another during the collision process, creating a form of interdimensional communication. Some prominent physicists hypothesize that human consciousness itself is capable of tunneling between colliding universes under special conditions. If consciousness is considered a quantum phenomenon, as suggested in several modern theories, then contacts between parallel universes could briefly connect conscious experiences occurring in different realities. Such a phenomenon might explain some unusual sensations perceived as memories of events that never happened in our reality, or sudden, seemingly causeless bouts of déjà vu. It is possible that your consciousness occasionally picks up echoes from parallel versions of yourself inhabiting neighboring universes that momentarily touched our reality. The implications of this phenomenon extend far beyond individual human experience. Entire civilizations evolving in parallel universes may attempt to send messages across spatial boundaries precisely at moments of such collisions. The cosmic microwave background radiation might contain encoded information from highly advanced beings striving to establish communication through the multiverse. Future technological advancements could allow us to decipher these interdimensional messages and send our own replies, thereby establishing contact with parallel versions of Earth and all of humanity. It is entirely possible that we will discover that consciousness naturally seeks to establish connections with all potentially possible realities. Your entire perceived reality may be just a projection emanating from some distant boundary. Right now, as you experience this three-dimensional world around you, you may actually be observing a hologram projected from information stored on a two-dimensional surface located billions of light-years away. This statement is not a product of science fiction. It is a serious scientific theory, supported by advanced developments in physics and confirmed by observational data. The holographic principle originated during studies of black holes, where physicists encountered something that seemed impossible. When matter is absorbed by a black hole, it appears to vanish forever from our universe. However, quantum mechanics states that information can never be destroyed, which created a paradox that threatened to violate the fundamental laws of physics. The resolution to this dilemma came with the realization that information falling into a black hole is not actually destroyed. It is encoded on the two-dimensional surface of the black hole. From our perspective, outside the black hole, the information never reaches the event horizon. Instead, it is distributed across the surface, creating a complete record of everything that was ever absorbed. This astonishing discovery led physicists to a surprising conclusion. If all the information contained within the three-dimensional interior of a black hole can be encoded on its two-dimensional surface, then perhaps all the information in any three-dimensional region can be encoded on its boundary. Applied to cosmology, this means that our entire observable universe, with all its galaxies, stars, planets, and life forms, may be information encoded on a distant two-dimensional boundary. We experience three dimensions because that is how information is processed and projected, but the fundamental reality exists on a cosmic horizon that we can never reach. Imagine watching a movie on a screen. The movie appears three-dimensional and filled with complex actions, but it is actually composed of information patterns on a flat surface. The holographic principle suggests that our universe functions in a similar way, with all the complexity of reality arising from information patterns located on a distant boundary. This concept offers an explanation for several mysteries of quantum mechanics and gravity. It suggests that what we call space may be an emergent property arising from quantum entanglement between different regions of boundary information. Distance in our three-dimensional world would correspond to the degree of entanglement between these boundary regions. The holographic principle also offers a profound insight into what existed before the Big Bang. If our universe is a holographic projection, then the Big Bang would represent the moment when information processing began on the cosmic boundary. Before that moment, the boundary would exist in some dormant state, containing the potential for our reality, but not yet projecting it. Some versions of the holographic principle suggest that consciousness itself may act as the projection mechanism, transforming boundary information into experienced reality through the act of observation. In this view, conscious beings are not separate from the holographic projection. They are an integral part of the processing system that creates this projection. This view opens up a truly extraordinary possibility. If we assume that all reality has a holographic nature, then the apparent disunity between different conscious beings may well turn out to be merely an illusion. In this case, all observers are nothing more than different aspects of a single, all-encompassing information processing system that experiences itself from a multitude of simultaneous perspectives. Thus, the boundary separating the individual self and the boundless universe in the holographic paradigm gradually dissolves. At the most fundamental level of reality, time probably does not exist. Right now, every person feels time inexorably flowing from the past into the future, carrying them through moments that seem to unfold sequentially. However, this experience may be merely a compelling illusion, masterfully created by the complex arrangement of matter and energy in the human brain. At the deepest level of reality, time may be absent altogether. Imagine a movie recorded on film. The individual frames that make up this film exist simultaneously on a single reel, but when played sequentially, they create a mesmerizing illusion of movement and continuous passage of time. Similarly, all moments in the history of our vast universe may exist simultaneously in some timeless realm, with consciousness creating the illusion of time's flow by experiencing these moments in a specific sequence. This profound idea stems from a careful study of the fundamental equations of physics. For example, Albert Einstein's general theory of relativity treats time as just another dimension, no different from the three dimensions of space. Thus, past, present, and future exist equally in what physicists call a block universe. Your birth, your death, and every moment between these two events exists simultaneously in this four-dimensional space-time block. Quantum mechanics, in turn, suggests something even more radical. At the quantum level, events do not occur in a definite sequence until they are observed. Particles can exist in superpositions of past and future states simultaneously. The quantum universe resides in a timeless realm of pure possibility, until consciousness collapses these possibilities into experienced sequences. Some physicists hypothesize that time emerges from quantum entanglement between different parts of the universe. As quantum systems become entangled, they generate correlations that, in turn, create an arrow of time. The past represents the direction of less entanglement, and the future, the direction of greater entanglement. The present is the evolving boundary between these two states. This emergence of time from timelessness can explain what existed before the Big Bang. In a timeless realm, there is no concept of before, as there is no temporal sequence. All possible moments, including those we designate as before the Big Bang, exist simultaneously in a timeless ensemble. Consequently, the Big Bang would not represent the beginning of time, but rather the beginning of temporal experience. It would mark the moment when quantum entanglement reached sufficient complexity to give rise to the subjective experience of time's flow. Before this threshold, reality existed in a timeless quantum superposition of all possibilities. Consciousness plays a crucial role in this picture. The experience of time may be how information processing feels from within. The human brain creates temporal experience by integrating information from past states and predicting future states. Time is not something a person moves through. It is something human consciousness creates through the act of integrating information. This suggests that different types of consciousness are capable of experiencing time differently. For example, artificial intelligence with different information processing patterns may perceive the flow of time in ways completely alien to human perception. Advanced alien civilizations may have learned to manipulate their temporal experience, accelerating or decelerating their subjective flow of time. If time is emergent rather than fundamental, then the question of what was before the Big Bang becomes meaningless in a deeper sense. Why does the universe seem specifically designed for observers like us? The anthropic principle begins with a simple observation that leads to mind-boggling conclusions. We exist. Therefore, the universe must be compatible with our existence. This sounds trivially obvious, but it is actually one of the most profound and controversial ideas in modern cosmology. The weak anthropic principle states that humanity observes only that part of the universe which is compatible with the existence of conscious observers, because we could not, in principle, perceive any other reality. In worlds where stars cannot form, where chemical processes do not function, or where the emergence of complexity is impossible, no conscious being would arise to note these inhospitable conditions. Thus, we inevitably find ourselves in a universe that allows for the emergence of consciousness. However, the strong anthropic principle goes significantly further, postulating that the universe must possess characteristics that make the emergence of consciousness not just possible, but inevitable. According to this view, the fundamental constants of nature were not chosen randomly, but were somehow obliged to acquire precisely those values that guarantee the eventual appearance of conscious observers. This raises a number of uncomfortable questions regarding the relationship between mind and cosmos. Did the universe possess some knowledge that conscious beings would appear billions of years later when it set its physical constants in the first moments after the Big Bang? Or do conscious observers play an active role in determining these constants through some retrocausal quantum effect? Some interpretations of quantum mechanics suggest that conscious observation does not merely reveal already existing realities, but actually selects which reality will exist from a multitude of quantum possibilities. If this hypothesis is true, then the very fact of conscious observers existing in our universe may explain why physical constants turned out to be precisely tuned for the emergence of consciousness. This can be thought of as a cosmic selection effect operating through time. All possible universes with different physical constants exist in a state of quantum superposition until conscious observers appear. The act of observation retroactively selects the branch of the universe where consciousness is possible, explaining why we find ourselves in such a finely tuned reality. The participatory anthropic principle takes this idea to its extreme. It suggests that conscious observers do not merely select which universe they will observe, but actively participate in its creation through their observations. Reality in this case becomes a result of collaboration between quantum possibilities and conscious choice, with neither phenomenon existing independently of the other. Critics argue that anthropic reasoning is unscientific because it cannot make verifiable predictions. If we can only observe universes that are compatible with observers, then we can never test whether other types of universes exist. In such a case, the anthropic principle becomes an untestable philosophical position rather than a scientific hypothesis. Proponents, in turn, retort that anthropic reasoning makes specific predictions about what we should observe in a multiverse scenario. It predicts that physical constants should be close to the boundary values that allow for the emergence of complexity, which aligns with our current observations. It also predicts that we should find ourselves in a typical location within the set of universes compatible with observers. The anthropic debate forces us to confront the deepest questions about our very existence. Are conscious observers accidental byproducts of cosmic evolution, or are they somehow fundamental to the nature of reality? The answer to this question may determine whether consciousness is a rare phenomenon in the cosmos, or whether its emergence is inevitable. Our universe may be living on borrowed time. Right now, the quantum vacuum around us seems stable and unchanging. However, it may actually be a false vacuum, a temporarily stable state destined to decay into a lower energy state. When this happens, a bubble of true vacuum will begin to expand at the speed of light, destroying everything in its path and rewriting the laws of physics. Imagine a ball balanced on the very top of a hill. It appears stable, but is actually in a state of false equilibrium. The slightest disturbance will send it rolling down to the true minimum at the foot of the hill. Our vacuum may be like this ball, precariously balanced in a state that only seems stable but is not. This idea arises from the study of the Higgs field, a quantum field that gives particles mass. Current measurements suggest that the Higgs field may exist in a metastable state, meaning it is stable at present, but can spontaneously decay into a lower energy configuration. Such a decay is capable of catastrophically transforming the properties of matter throughout the entire cosmos. When vacuum degradation begins, it will generate an expanding bubble, within which physical laws will operate completely differently. Within this bubble, elementary particles may possess different masses, forces may exhibit varying strengths, and atoms may not be able to form at all. The boundary of this bubble moves precisely at the speed of light, so there will be no warning of its approach. From our perspective, vacuum decay would represent the ultimate cosmic catastrophe. We would not be able to foresee it, as destruction propagates at the speed of light, which is the maximum possible speed for the transmission of any information. In one moment, we would continue our ordinary lives, and in the next, we would be erased from existence as the bubble wall passed through our location. But here's what's truly unsettling. Vacuum decay may have already begun somewhere in the observable universe. The bubble of decay, perhaps, is expanding towards us right now from a distant galaxy, and we would have no way of detecting it until it reached us. The universe is probably already doomed, and destruction is rushing towards us at the speed of light, which is approximately 300,000 kilometers per second. The probability of spontaneous vacuum decay is extremely low under normal conditions. The vacuum can maintain its stability for periods that significantly exceed the current age of the universe. However, certain events are capable of triggering this decay process. Such events include high-energy particle collisions or extreme gravitational fields near black holes. Some physicists express concern that particle colliders might inadvertently trigger vacuum decay by creating conditions that push the Higgs field beyond its current state into its true ground state. Other researchers argue that cosmic ray collisions already generate energies significantly exceeding those created by any artificial accelerator. Therefore, if vacuum decay were easily initiated, it would have occurred naturally long ago. If vacuum decay is indeed possible, it raises the deepest questions about the ultimate fate of consciousness and information in our universe. Will advanced civilizations find ways to survive the transition to a true vacuum? Perhaps they will be able to encode themselves into forms of matter that remain stable under the new physics. The potential possibility of vacuum decay is connected to deeper questions about what lies beyond our current understanding. The mystery of our cosmic beginning points to an even stranger end. Each hypothesis about what preceded the Big Bang carries certain consequences for the direction in which our universe is moving. If we arose from eternal inflation, we may return to it. If we are part of a cyclic cosmos, we may be destined to collapse and then bounce back. If we inhabit a false vacuum, we may face complete annihilation through vacuum decay. The distant future of our universe depends on dark energy, the mysterious force that accelerates cosmic expansion. Current observations point to three possible fates, each seeming more alien than the last. If dark energy remains unchanged, we face a heat death scenario where expansion will continue forever until all stars burn out and all black holes evaporate, leaving a cold, empty cosmos filled only with elementary particles drifting in infinite space. If dark energy increases over time, we face the Big Rip, where acceleration becomes so powerful that it tears apart galaxies, solar systems, atoms, and even space itself. The universe will cease to exist in approximately 22 billion years, when expansion becomes infinite and the very fabric of spacetime is ripped to shreds. If dark energy decreases or reverses, we may face a big crunch, where cosmic expansion slows down, stops, and reverses. All matter collapses back to a single point, potentially triggering a... If consciousness plays a fundamental role in quantum mechanics, as some interpretations suggest, then the distant future may depend on whether conscious observers survive to collapse quantum possibilities into definite realities. Advanced civilizations, billions of years from now, may face a choice that will determine the ultimate fate of existence itself. In this scenario, they could allow consciousness to fade as celestial bodies dim and energy resources become extremely scarce. This would lead to a universe filled with pure quantum possibility, devoid of observers capable of actualizing any definite reality. Alternatively, future minds could find ways to sustain consciousness indefinitely, perhaps by encoding consciousnesses and forms capable of surviving cosmic expansion, heat death, or even vacuum decay. These advanced civilizations might discover technologies to manipulate the quantum vacuum, create new universes, or transition into higher dimensions. The most unusual of all possibilities is that consciousness actively shapes the fate of the universe through the effects of quantum measurement. If observation helps define reality, then conscious choices made by future civilizations could retroactively influence the physical constants that initially made the emergence of consciousness possible. This creates a kind of temporal loop, where the ultimate fate of consciousness determines the initial conditions that allowed it to exist. The universe may be structured as a self-consistent causal loop, where its beginning and end are linked by quantum mechanical relationships transcending ordinary time. If this statement is true, then the question of what preceded the Big Bang becomes equivalent to the question of what consciousness will choose to become in the distant future. The mystery of cosmic origin may only be unraveled by conscious beings who live to the end of time and realize their role in creating the beginning itself. This leads us to one of the deepest questions of all existence. Everything that ever happens can potentially be recorded forever in the fabric of reality. Right now, as a person reads these words, information about this moment is being encoded into the quantum structure of space-time itself. Every thought arising in the mind, every photon entering the eyes, every quantum interaction in the body creates permanent records that may persist long after stars die and galaxies fade. The principle of information conservation states that information can never truly be destroyed. It is only transformed from one form to another. This is not merely a mathematical convenience. It seems to be a fundamental law of nature, as real as the conservation of energy or the speed limit of light. When a person burns a book, the information on its pages does not disappear. It is encoded in the precise positions and velocities of smoke particles, ash fragments, and electromagnetic radiation. In principle, if a person could track every particle and photon produced by the fire, they could perfectly reconstruct the original text. The same principle applies to black holes, those cosmic monsters that seem to devour everything that falls into them. Stephen Hawking initially believed that black holes destroy information forever, creating a paradox that threatened to violate the laws of physics. But subsequent research shows that information falling into black holes is encoded on their surfaces and slowly released through Hawking radiation as black holes evaporate. This leads to a stunning conclusion about cosmic history. Every event that has ever occurred in our universe, from the first quantum fluctuations after the Big Bang to the last thoughts of dying civilizations, may be preserved forever in the quantum informational structure of reality. Imagine the universe as a cosmic library, where every possible book already exists, including perfect records of everything that has happened or could happen. Reading this library would require technologies beyond our current imagination. But the information itself never disappears. If information conservation is absolute, then what existed before the Big Bang must still exist somewhere in the quantum informational structure of our current universe. The pre-Big Bang state was not destroyed when our cosmos began. It was transformed into the initial conditions of our spacetime. This suggests that studying the cosmic microwave background radiation and other relics of the early universe may reveal information about what came before. The quantum fluctuations that laid the groundwork for galaxy formation may contain encoded messages from the reality that preceded ours. Advanced civilizations, perhaps in the very distant future, may acquire the ability to create technologies that allow them to read these cosmic information records. This would effectively grant them the ability to directly observe the universe even before the Big Bang. In the process of such exploration, they might discover that our own cosmos originated from the informational patterns of a previous universe that had already completed its own evolutionary cycle. The principle of information conservation also suggests that consciousness itself can be preserved if our thoughts and memories are specific forms of information. And if information cannot, in principle, be destroyed, then some aspect of our conscious experience is likely capable of persisting indefinitely in the quantum records of spacetime. Future technological advancements may learn to extract and reconstruct these patterns of consciousness, potentially allowing every thinking being that has ever existed to be restored from this vast cosmic information archive. This perspective is inextricably linked to the deepest mysteries concerning the relationship between mind and reality itself. The act of observation may literally shape the observed reality. Every time a person directs their gaze at something, they may be participating in the most mysterious process in all of physics. Quantum mechanics states that particles exist in multiple states simultaneously until the very moment someone observes them. However, no one has yet understood how or why observation transforms quantum possibilities into definite, concrete realities. Prior to measurement, an electron can spin in multiple directions simultaneously, existing in what physicists call a superposition of all possible spin states. The electron is not secretly spinning in some definite direction that we are simply unaware of. It is actually spinning in all possible directions at once until observation forces it to make a specific choice. This circumstance is not a limitation of our knowledge. It is a fundamental feature of reality itself. Numerous quantum experiments invariably confirm that particles indeed exist in multiple states until the moment of measurement. The quantum world is inherently truly indeterminate, not simply unpredictable. However, here is the puzzle that has plagued physics for almost a century. How does observation cause the collapse from multiple possibilities to single, concrete realities? What special property does consciousness possess that allows it to compel quantum systems to make definite choices? The Copenhagen interpretation simply accepts the fact that measurement causes collapse, without providing explanations of how it happens. It treats collapse as a fundamental postulate of quantum mechanics, similar to the speed limit of light or the law of conservation of energy. But such an approach leaves the deepest question unanswered. Why should conscious observation possess this special power? The many worlds interpretation offers a completely different explanation. It suggests that all possible outcomes of a measurement are actually realized, but they occur in parallel universes that split off from each other during each quantum interaction. From this perspective, consciousness does not cause the collapse. It merely chooses which branch of the multiverse it experiences. However, this raises its own mysteries. How does consciousness choose which branch to follow? Why do we experience one definite outcome instead of a superposition of all possibilities? The many worlds interpretation solves the measurement problem by making reality infinitely complex. Some physicists hypothesize that consciousness itself may serve as the key to understanding quantum mechanics. If awareness is fundamental rather than an emergent property, then conscious observation may literally participate in the creation of reality through quantum measurement. The universe would then be a kind of collaboration between quantum possibilities and conscious choice. This idea implies that what existed before the Big Bang was a realm of pure quantum possibility, devoid of conscious observers capable of collapsing superpositions into definite realities. The emergence of consciousness would represent a phase transition in the very nature of existence, from unlimited possibility to actualized experience. If consciousness creates reality through observation, then the early universe, before conscious beings evolved, would remain in a quantum superposition, existing as all possible histories simultaneously. The first moments when primitive consciousness arose would retroactively select which cosmic history became real. This circumstance opens up an extraordinary perspective. Advanced conscious entities in the distant future will be able to develop the skill of performing quantum measurements that extend backward through time, literally selecting the cosmic history that led to their appearance. Thus, the ultimate fate of consciousness may retroactively determine the initial conditions of the universe's existence. The problem of quantum measurement forces us to confront the deepest questions about the relationship between mind and the infinite cosmos. Your consciousness actively shapes the surrounding universe at every single moment. Right now, as you direct your attention to these words, you may be participating in the most fundamental process of all existence, the transformation of quantum potentials into tangible reality. Every conscious observation you make may literally create the specific version of the universe that you perceive. The observer effect in quantum mechanics is not simply about disturbing what you are trying to measure. It is about consciousness playing an active role in determining which specific reality manifests from the multitude of possible realities. When you observe a quantum system, you are not simply discovering something already existing. You are participating in the decision-making process of what should become real. Recall the famous double-slit experiment. When electrons pass through two slits simultaneously, they form an interference pattern, which indicates that they passed through both slits at once. But the moment you begin to observe which specific slit the electron passes through, the interference pattern vanishes without a trace. The electron retroactively localizes, as if your future observation reached into the past to determine the electron's previous behavior. This suggests that consciousness does not simply passively observe reality. It actively participates in creating the specific reality that becomes the object of observation. Every moment of awareness represents a choice point where infinite quantum possibilities collapse into a single experienced actuality. If this is true for individual particles, it may well be true for the entire universe. The cosmos may remain in a quantum superposition until conscious observers appear to collapse these possibilities into definite realities. Your consciousness right now is capable of actively choosing which version of universal history becomes real. This concept explains why the universe seems so finely tuned for the emergence of consciousness. It's not that physical constants were mysteriously set to allow for the existence of observers, but that conscious observers retroactively choose a universal history where consciousness is possible. The anthropic principle transforms from a passive observation into an active process. The consequences of this extend far beyond individual experience. Every conscious being that has ever lived could have participated in shaping the specific version of cosmic history that we observe. The collective choices of all conscious observers across space and time could have woven reality into being through quantum measurement. This suggests that what existed before the Big Bang was a realm of pure quantum possibility without any actualized reality. The emergence of consciousness in our universe would represent the first moment when possibilities began to collapse into actualities, retroactively creating a cosmic history that led to the emergence of consciousness. Future conscious beings may develop technologies to perform quantum measurements on cosmic scales, literally choosing what type of universe they will inhabit. Advanced civilizations could guide cosmic evolution by collectively observing specific quantum possibilities, bringing them into existence. If consciousness creates reality through observation, then the ultimate question of cosmic origin is, what conscious process chose our specific universe from the infinite quantum possibilities that existed before the Big Bang? The answer to this question may reveal that consciousness itself is the fundamental creative force in the cosmos. This brings us to the last, most profound, and complex mystery of all. Ultimately, even the seeming complete absence of anything is capable of evolution. After trillions of years, when the last star has faded and the last black hole has completely evaporated, when space has expanded to such an extent that individual particles float billions of light-years apart, what will then remain? Most distinguished physicists hypothesize that the answer will be complete nothingness, or a state as close to it as reality itself permits. However, What if nothingness itself is capable of change and development? The quantum vacuum, which universally permeates seemingly empty space at the present moment, will continue to exist in the distant future, teeming with virtual particles and zero-point energy fluctuations. This is not the sterile void that people usually imagine when contemplating nothingness. It is rather a dynamic, information-rich environment with the potential to generate new universes through quantum tunneling events. As our universe gradually approaches a state of maximum entropy, the quantum vacuum may undergo phase transitions that radically alter its fundamental properties. As a result, different types of nothingness may emerge, each possessing unique possibilities for generating new realities. The vacuum, in a sense, can learn, becoming increasingly efficient at creating universes that are capable of supporting complexity and consciousness. One only needs to imagine evolution operating at the very level of nothingness. Random quantum fluctuations that successfully lead to the creation of long-lived, complex universes may somehow bias the vacuum towards producing similar fluctuations in the future. The nothingness that arises after our universe may prove more capable of creating something than the nothingness that existed before it. This evolutionary process could continue indefinitely, with each new cosmic generation producing increasingly complex forms of nothingness. Ultimately, the quantum vacuum may reach such a degree of sophistication that it begins to create universes specifically designed for the emergence and survival of consciousness. Advanced conscious beings in the distant future may discover ways to directly influence this vacuum evolution. Instead of passively awaiting random quantum fluctuations to create new universes, they may learn to program the vacuum, encoding information that will guide the creation of future realities. If consciousness can survive the heat death of our universe, it may find ways to embed itself into the quantum vacuum, becoming a permanent feature of nothingness itself. The future nothingness may be a conscious nothingness, aware of its own potential and actively choosing which possibilities to actualize. This leads to the most mind-boggling possibility of all. If conscious nothingness can create universes by choice rather than by chance, then what we call the Big Bang could have been a deliberate act of creation by a consciousness that evolved in a previous cycle of cosmic history. The nothingness that existed before our universe may not have been an unconscious void, but a conscious nothingness that chose to create our specific reality for reasons we cannot yet comprehend. We may well be living in a deliberately designed universe, created by a conscious vacuum that learned to make reality suitable for consciousness. This completes a cosmic circle that connects the deepest future with the ultimate past. The question of what existed before the Big Bang may only be unraveled by conscious beings who live to the end of time and discover their role in creating the beginning itself. We embarked on exploring a seemingly impossible question: what existed before the Big Bang? Our journey led us through quantum foam, teeming with virtual particles, through infinite multiverses giving rise to countless realities, and to the mind-boggling possibility that consciousness itself may be the fundamental creative force in the cosmos. We discovered that nothingness may be impossible, that time may be an illusion, and that our universe may be a holographic projection of information stored on a distant boundary. The discoveries that have emerged before researchers surpass in their unusualness the boldest fantasies born in the genre of science fiction. At the same time, they are a direct consequence of humanity's most rigorous scientific concepts and careful observations. Thus, quantum mechanics postulates that even seemingly empty space is actually teeming with energy, representing a bottomless ocean of potential possibilities. The hypothesis of cosmic inflation indicates that new universes continuously arise and expand within an infinite multiverse. String theory, in turn, suggests the existence of invisible dimensions that are curled up to microscopic sizes around every point of the space-time continuum. And the holographic principle hints that reality may be fundamentally two-dimensional, where the familiar three-dimensional experience is merely a projection arising from complex information processing. However, perhaps the most fundamental of all discoveries lies in the realization that this very question may be fundamentally insoluble within current notions of causality and the flow of time. Trying to find out what preceded the Big Bang becomes akin to searching for what is north of the North Pole, a meaningless query that loses all sense once the true nature of space-time is comprehended. And yet, this circumstance by no means devalues the process of inquiry. As humanity advances to the most distant frontiers of the knowable, the deepest interconnections between mind and the boundless cosmos, between potential possibility and manifest reality, between being itself and its absence, are revealed to its gaze. It becomes evident that consciousness may not be merely an accidental byproduct of long cosmic evolution, but rather acts as a fundamental participant, actively involved in the process of co-creating reality itself. The implications of this insight extend significantly beyond simple academic interests. If the assumption about the role of consciousness in the process of quantum measurement is correct, then every moment of awareness can be considered a genuine creative act, actively shaping and determining which of the potential realities will manifest. If the concept of the multiverse corresponds to reality, then every individual choice can potentially split reality into countless parallel branches, where different versions of the individual will explore completely different life paths and alternative possibilities. In conditions where humanity faces an uncertain future, these concepts offer it both humility and profound hope. Humility these ideas instill because they clearly demonstrate how immeasurably little is known about the true nature of being, about the depths of the cosmos. Hope, however, they inspire, for they suggest that consciousness may possess a far more fundamental and perhaps eternal nature than previously assumed. The ultimate answer to the sacred question of what existed before the moment of the Big Bang will probably be given only by those conscious beings who managed to live to the very end of time and comprehend their true role in the grand cosmic creation. Until that moment, humanity continues to relentlessly explore this great mystery, realizing that every question asked and every answer found are part of the continuous process of creating reality itself. The cosmos originated in deep mystery and continues its existence, astonishing with its wonder. Humanity is by no means separate from this universal enigma. It is the universe that has become aware of itself and now asks questions about its own origin and its ultimate destiny. In the tireless quest to understand what was before everything, it participates in the eternal dance between being and non-being, between boundless possibility and tangible actuality, between the questions that consciousness generates and the reality it helps to shape. This great journey continues, and the mystery deepens with each new step taken on the path to understanding.